Hi, everybody, again, and welcome to the second part of chapter 21. So far, we covered quite a bit basically in this chapter. We introduced the electric charge. We also introduced the law of Coulomb, which gives me the force if between 2 point charges. That's a critical point in here. This is not between anything. You have a point charge, Q1, and you have point charge, Q2, and you happen to know the distance between them, basically the vector that links the 2 point charges. Think of them as point particles from your class of mechanics, from your physics 4B, 4A, I'm sorry. So then we know the force, it's 1 over 4 pi epsilon naught. For all practical purposes, that's a number, at least in the vacuum and the air, to be 9 times 10 to the power 9. With the appropriate units, which is in Newton times meter squared divided by Coulomb squared. That's Newton's law, times the product of the two charges, similar to what you guys did in physics 4A, namely the gravitational force involves also the product of the two masses. This involves the product of the two charges. What is a charge? Fundamentally, it's just like a mass, basically. It's just a fundamental property, okay? Divided by the distance squared between them. And it's a vector because it's a force, and the vector points from basically one charge to the other. The forces are repulsive if the charges are of the same type, and they're attractive if the charges happen to be different signs. So that's Coulomb's law. And then basically we invented a new concept. We called it the electric field. And it turns out that that electric field I can measure just by taking a 1 Coulomb charge, test charge with me, and measure the force exerted on that 1 Coulomb charge. So the unit for the electric field are Newton per Coulomb. That's exactly what that means. And that's the concept that we've been dealing with so far. The electric field is crucial, assuming that I have distribution of some sort of charges. I can always find the electric field that they produce. Then, if in case I bring another charge to a point in space where I already measured the electric field there, I know exactly what force that charge is going to be subject to. So from that point on, I apply just the chapter 4 from physics 4A, namely go back into F equals to ma and solve for it, and can answer whatever other questions you ask about the mechanics of that specific point charge. So that's basically what we did. Then we started applying this thing, trying to find different ways of finding the electric field for different configurations. We said, okay, if I have two charges, I can find the electric field produced on by the two charges on a line. So if in case joining the 2 points, if in case I bring a charge anywhere on that line, I know exactly how much force that the two charges will exert on that third charge. Of course, we had to introduce the concept of superposition principle, which was an idea that we really need to calculate stuff. Without it, we cannot, because Coulomb's law links only 2 point charges. So if a third charge comes into the mix, or more than third charge come into the mix, Coulomb's law will not help you. So you need the second one. Remember, I said when we're solving problems, we need to justify our steps. That is exactly what I'm talking about. That shows deep understanding of what's going on. When you invoke Coulomb's law, you're invoking it in the pure form of it, which is just between 2 point charges. Now, if the problem involves more than 2 point charges, then your justification for the next level of applying Coulomb's law is to invoke the superposition principle, saying that this is a principle that works, therefore I'm going to use it. So you say by superposition, then you can start working your problem. So you're showing deep understanding of the concept. So we said, okay, we have 2 point charges. I want to find the electric field they produce. So what I'm saying is I will find the electric field for one of them, and I will find the electric field for the other one, and then add the two by superposition. So if I bring a third charge in there, to the point where I was calculating the electric field, I can find the force exerted by the electric field that these 2 point charges produce, okay? So that is basically what we did. We also did I think, so many examples last time, and I promised that we have more examples to do, okay? By the way, I corrected those percentages. They were already correct in terms of the Canvas. Canvas has already the assignment grouped by basically a type. So they were correct. All I did is translate it there so that you guys have that correction. So please take a note of it so that you know exactly what everything is weighing on what and so on and so forth. That's what you get sometimes when you copy and paste, because you copy from what you have been working on and then you paste it somewhere trying to get things done. But I fixed it, so that's exactly how much everything is weighed in there. Okay, so let's go back to where we were last time. Do you guys see my OneNote notes?
Yeah.
Okay, very good. So basically, this is the configuration we were in, I think, last time. If you can get my pen, where is he? Okay, does this give me? It says the draw tool. Okay, I don't know if this would work or not. Let's see here. Yep. Oh, I don't want to do that. That's a highlight. I'm sorry. I'm trying to get this thing done. Okay, so let me exit this thing in here and go into my OneNote tool. Okay, very good. So basically, this is what I was talking about. So you find the electric field in here, in point B, for example. And now, if you bring a third charge into the mix, you can find what the electric field. I didn't do it in here in the point C, but I assume it's not hard to do, because here is how you do it. First of all, you find this distance, which is given to you, 13 centimeters in a specific problem. And then this distance, which is also 13 centimeters. You know the charges, both of them happen to be 12 nanocoulombs from that example. All you're supposed to do in this case is find the electric field produced by the positive charge, which should point this way because it's repelling that, the electric field emanates from a positive charge, and the electric field points toward the negative charge. That's why the other one is pointing this way. The strengths are the same because the strengths, they depend on the electric charge, and the electric charge happen to be the same value, the same numerical value, which is 12 nanocoulombs. And also depends on the distance squared, 1 over the distance squared. And the distance is the same. So 1 over 4 pi epsilon naught is constant. So in this case, the vector length are the same. One of them is pointing upward, the other one is pointing downward with the same angle. So this angle must be the same as that angle, because again, the cosine of this angle is equal to whatever that ratio of this distance over that. And the same thing for this angle also, because that's somewhere in the middle there. That's the property of the triangle in this case. So the two values, they cancel in the y direction and they add up in the x direction. They add up in the x direction, and from there you're going to find the projection in the x direction and you're done. So we've calculated the electric field in the c direction. For further, basically specific calculations, I recommend you go and do this example 21.8 from the book. Okay, so these things are from the book. They are not something out of the book, so that you can... Sometimes I follow the book, sometimes I don't follow the book, to give you a different approach to the same problem so that you have an idea of where you are. I promised last time that there are more things to do in this case in here. Let me see here. Was it in this section or was it this section? Anyway, there are more things that we need to calculate from this chapter. So we really need to finish those calculations. Yeah, here they are. Okay, the things that we said we really need to do in order to close the book on this chapter. Before I do that, there are some key concepts. If you guys think I'm going too fast, please slow me down, okay? There is the concept of the electric field itself, that how do we represent the electric field? And that's something by itself. So I'm going to talk about that first, and then we're going to do the calculations in there, okay? When we do the chapter on Gauss's law, we're going to do the same calculations again, but using a different approach that it turns out to be a lot easier than actually doing it this way. So again, you're learning different techniques, trying to find the same thing. And you will find at some point one technique works better than the other. Sometimes one technique does not work at all. So you're going to resolve back to the fundamentals, okay? You will learn that Gauss's law only works in the case when there is symmetry. If there is no symmetry, then Gauss's law will not be able to help you. So you have to go back into what we're doing right now. That's basically why you have to do it this way. There is actually another approach, a third method involving the electric potential, which we're going to define later on. And that works also similar to what we're doing, except you don't have to deal with the nastiness of the vectors. So you don't have to, just dealing with numbers. So it's a little bit easier, if you wish, doing it that way. So again, you'll be empowered with different techniques to find the same thing, because ultimately, again, the goal is to find E. Once I find the electric field, and then you bring a charge into the mix, that charge times E will give me the force. And we go back to where we're supposed to be to doing this problem. So all of our goal right now is to find what this force is. This expression of the force, which was a definition with which we define the electric force, the electric field, I'm sorry, is part of what is called as Lorentz force. So when you hear the Lorentz force, it has two components. This is one of them. There is another one that involves the magnetic field that we're going to talk about later on. After we find the magnetic field, then we combine the two and say, okay, the electromagnetic force has this component, which is the electric part of it, which is this one, and the magnetic force is coming from this one. So if this one, if you wish, is half Lorentz force, or full Lorentz force in the case there are no magnets present. So that's basically what this is. So this is a Lorentz force that we're dealing with. So if you hear me say the Lorentz force, that's exactly what this expression is. So it's another version of Coulomb's force, if you wish. So let's first of all represent the electric field, as I said, for a point charge. And I already expressed that. So I have a point charge in here, positive charge. And if I express the expression for the electric field, then here in this case, it's 1 over 4 pi epsilon naught times the charge itself, Q, divided by the distance squared times the radial hat. Because if I'm calculating it in here, it's going to be pointing away from the charge. If I move on a sphere, not a circle, I'm representing on the circle because I cannot really draw a sphere. Nobody can, at least on a flat surface. So it's going to point away from it. So any point in here is going to be this way. And it's the same strength because it depends only on how far you are. So if you are on a sphere of the same radius, R does not change. So what changes in this case is just the direction. Since the direction changes, it changes only with R hat. So it's going to point away. So the electric field is pointing away all the time. You have to imagine with me that this is a sphere, not a circle. There is a distinction between the two. A sphere is a three-dimensional object. So anywhere on that sphere, the electric field will point away from the charge because it's a positive charge. Had it been a negative charge, it's going to point inward. Because if I bring a positive 1 Coulomb in here, so now I bring 1 Coulomb to find the electric field in there. That electric field, I'm sorry, that 1 Coulomb will be subject to a force, which is this electric field times 1, because I brought 1 Coulomb, times 1. And because it's a repulsive force, this is a positive charge and 1 Coulomb is positive, so it's going to repel it. So it's going to point outward. If the charge, though, was negative, that created the electric field. If the charge itself is negative, and I bring 1 Coulomb, which is a positive charge, the force is going to point inward. The charge is going to try to go into it because it's an attractive force. So the electric field now will be radial also. It depends only on 1 over the distance squared. But it's going to point toward the negative charge. Okay? And again, this is on a sphere, not on a circle. Because this is in space, not on a surface. So when you bring a charge, it's going to be in space. So it's going to influence the entire area, not just there is no specific direction with which it's going to act. It acts in the entire space. So it's going to be a three-dimensional object. So think about it. So now I'm going to go back into my positive charge. Unless otherwise told, you always take a positive charge as your point. So if I'm very close from it, remember this depends on 1 over r squared. If I'm very close from it, the electric field is going to be very big because this number is going to be very small, and you divide by a small number, you're going to have a big number. Okay? Then if I move away from it, if R is far from the charge, then this number is bigger. So when you divide by a big number, squared by the way, it's going to be smaller. So the electric field will be a smaller and smaller arrows pointing away from the charge, because I took a positive charge. Had I taken a negative charge, it's going to be arrows pointing toward the charge, but they're going to be stronger, the closer I get into the charge. Weaker and weaker, the further I get into from the charge. Okay, so now we have a way of representing the electric field, because I took these 2 points in here, but there is another point in between them. I could have drawn this one. The magnitude of that point is smaller than the first one, but bigger than the second one. But still, between every 2 points, there is another point. There is another one in here whose magnitude is bigger than the third one that I drew, but it's less than the first one. So instead of doing this, what I'm going to do is I'm going to draw the whole, basically all the points in space. So I'm going to go back into a positive charge and draw an arrow for the electric field pointing outward, because any point in space can be a point where I can calculate the electric field. So basically at this point now, I have drawn the entire electric field just on a single line. What I lost in comparison to this one gives me actually a visual. I can see this electric field versus this electric field, for example. In this point and in that point, it's the same electric field, but calculated in this point closer, it's longer than calculated near it. So I can tell the intensity of the electric field just visually. Here I cannot. In the second representation, I lost that capability, but I gained something in the process. I gained the fact that the entire space is affected, that there is no special case about this point and the other point. Both points have the same basically distinction. As a matter of fact, there are an infinite number of points between them and outside of that range that I really needed to represent. And the second representation give me that. You see? So both of them have strength and weaknesses. One of them, this one, its strength, it shows me the magnitude of the electric field. Whereas this second one shows me the fact that the electric field, did I say magnetic field? I'm sorry. The strength of the electric field, yes. So the first one shows me the magnitude of the electric field, how strong it is. I can tell just by looking at the length of the vector. Whereas this one gives me an additional benefit in the fact that I can tell that the electric field, where it exists in the entire line, but I lost the sense of its strength because it's only one line. You guys see that? In order to recover the strength again, we come up with an invention, basically. And the invention is the following. Because I know the following. I know if I double this charge, because remember, the electric field also depends on the charge, depends on Q itself. If I double this charge, this lines also will double in length. So I have that addition. In here, if I double the charge or triple the charge or quadruple the charge, the line is a line. You cannot make an infinite line is an infinite line. When you multiply infinite by 2 or by 3, it doesn't matter. It's still infinite. So I cannot tell that from this second one. But in here, I can clearly see that. If I double the line, double the charge, I can see the lines extending in length. If I take this charge and divide it by 2, I see the length also start to shrink. They still shrink accordingly. This one shrinks by half and this one shrinks by half too. But they still keep that notion that the closer you are from the charge, the stronger it is. So there is some strength in this one that the other one doesn't have. So in order to recover that, and of course this one has its own strength, which is the fact that the electric field is represented everywhere, as it should be, because this one doesn't. This one doesn't show you the electric field everywhere. It shows you only specific points. So in order to recover that, we're going to do something. We're going to come up with a new concept, which is really the density of lines. Meaning, we're going to come up with an agreement, and the agreement is of for a unit charge, we're going to draw a certain number of lines. Let's say, for example, 4, like I'm doing right now. It doesn't matter how many. Let's say 4. Then if you double the charge, double the number of lines. That's all. So right now, this electric field, for example, for Q, so if you see me draw twice as many lines, that means, hey, this charge is more than the first one. That's all. If I weaken that, then that means draw less lines. That's all. However you agree to draw for 1 Coulomb, draw as many for whatever charges you have. There is no set number that you can do. You can do whatever you want to. So we recover now the strength using the concept of the density of field lines. These are called field lines, by the way. And their density, which is how many field lines penetrate a given surface area. The reason why I'm saying it's a surface area, because I'm going to go around this and draw a whole sphere, not a circle, a sphere, okay? And calculate how many field lines penetrate a single unit of surface area, a square meter, for example. So I come in here and find a square meter. This is 1 meter squared, and count how many lines go through it. If you double the charge, this should double. We should see doubling of these field lines. If you triple the charge, 3 as many field lines go through it. If you take that number of charges and divide it by 10, you should see the 10th of the field lines go through it. So the density of field lines per unit area. Density of field lines per unit area represent the strength of the electric field. Represent the strength of the electric field. So now, this picture works now, as long as we have that in mind. This is the way we represent the electric field. A whole line, okay, going from one charge to infinity for a positive charge, or coming from infinity toward the charge for a negative charge, and then agree to draw the field lines and calculate the density, how many field lines go through unit area. Okay, that's it. Now we have recovered the strength again. So this picture works for both of them. So this one now, we don't need to use it anymore. And we just stick with the second one, and the second one will give us everything, as long as we have that convention in mind, as long as we have that agreement in mind. So we would just draw a whole field line, basically, that goes from end to end, and agree to draw as many per unit area. So you're asking yourself, for example, how many should I draw for 1 Coulomb? It's up to you. Doesn't matter. That's a convention. You draw 10, for example, or draw 123. Doesn't matter. Whichever number comes to your mind. As long as you stick with that number, though, then you're fine. Actually, you can, by convention, people, to make the math easy for themselves, they draw 1 over epsilon naught, which is of the order of billion, basically, 10 to the power 9. You're asking why exactly 1 over epsilon naught? Because later on, when we go through Gauss's law, you see that the epsilon naught will cancel everything, okay? So that's fine for right now. But since you have the freedom to choose whatever you want to, why not 1 over epsilon naught, just like any other number? So basically, for right now, we're going to stick with any number. We don't have to go with this specific number, as long as we have that in mind. That is how many field lines penetrate a given surface. That is really the key in here. That's going to represent the electric field. Okay, I think I gave it more than its fair shake in here in terms how to visualize the electric field and interpret the field lines, the electric fields. Okay, so at this point, we will come to this point, by the way, a lot in the next chapter. So I'm not going to spend more time on it because we have other things to do too. Is this clear to some extent? I know one of you earlier raised an issue with the speed, and yes, okay. The advantage of having this session recorded is twofold. First of all, it gives you a chance to go back into the material basically, and since you know when we discussed what, if it was in the beginning, I know they're over an hour long and probably you don't have that much time to do things, but if something is not clear to you and you know it happened in the beginning, so that you can go into the beginning and start going through it again and make sure that you have a full, now we have the caption, the closed caption, so go through it and see if everything makes sense to you. So that's good. That's one thing that we gain from these recordings. The other thing that we gain from recordings also is a chance for me to go through the materials too again, and sometimes I make mistakes. Actually, not sometimes, a lot of times I make mistakes. So in the next lesson, I try to catch up with these things. It doesn't mean that during the live session we don't catch them. Please do. If you think that something is not right, like I said, I make mistakes all the time. Please try to correct them and tell me, okay, I think there is something wrong in there, or there is a different approach to that, or maybe it's not clear or something. Please intervene in there, okay? So don't let it there. And if you find it after the class, I really don't take any offense to it whatsoever. I have my degree, nobody's gonna take it away from me, so I'm not really going to feel bad or sorry or something like that. No. If you find that something is not right, it was not cleared, it was not defined correctly, or it was not done correctly, please let me know, so that we have to correct it and we fix it, okay? So that's really, I'm not gonna be offended whatsoever. As a matter of fact, I encourage that. Sometimes, by the way, I make mistakes in purpose to see if you guys are following me or not. So I'll try to trick you into something, so please follow me so that we correct that right away. And sometimes, honestly, and most of the times, actually, it happened by itself. So you really need to, it's a lack of focus or whatever. So that's the thing I wanted to say about this recordings. I really like the fact that they're recorded. It gives you a chance to go through the materials again and again, just in case if something is not clear. And you still should ask questions to clarify things. And also it gives me a chance to go to the same thing too, okay? So this is one of the points that we're supposed to cover in this material in here. Let me go back into my notes. So let me go through the calculation for the ring. Before we do the ring, we have to do the line segment first. I think it's more appropriate to start with the line segment. Then we do the ring, then we do the disk, and they follow one each other. Ring and disk, they derive of each other. And then we're gonna go with the infinite plate, okay? Let me start a new blank sheet in here. So first of all, the electric field produced by a wire of length, doesn't matter, let's take it to A. So it has a negative A from one side and positive A from the other side. And I'm going to go into the middle, somewhere in the middle, I'm trying to find at a distance Y from the wire. So this is position 0, by the way. I want to find the electric field in that point produced by this wire. Again, what happened to this wire is we sprinkle, we throw, okay, or we charge it by an amount Q. So we take a Q charge and we dump it on the wire, uniformly though. Okay? So what it means is there is a uniform distribution of charge on the entire wire. So if I take an element of it, it will have a small amount of charge. Overall, it has a Q charge. Okay, so that's basically the setup for the physics of this problem. So that means that the entire charge now is spread uniformly throughout the entire length of this wire, which is 2A, by the way. Okay? And the distribution in here is defined by lambda. Lambda is the amount of charge that I'm going to sprinkle per unit length, meaning lambda is just Q over the distance, that's all, okay? So if I go an X distance from the origin, this point in here, X from the origin, and a slightly bigger than that, which is X plus dx. So this length is dx. So I took a dx element of the wire, not the entire wire, just a dx of it. I know per unit length I have lambda coulombs per meter, but I didn't take a whole meter, I took just a dx of it. So if I go back into my definition of what uniform distribution is, that means this lambda is constant. That's what uniform means, okay? It's not like a baseball bat where, for example, on one side it's smaller and the other side is bigger, this distribution of mass per unit length, so the mass on this side is less than the other side. Think of it as a rod, for example, that has the same distribution of mass, except in here, instead of mass, we're talking about charge, okay? So instead of kilogram per meter, we're talking a Newton per meter, I'm sorry, coulombs per meter, okay? So in this case, the charge on a dx is going to be dq, and that dq is the charge per unit length times the length we're considering, which is just dx length. So the dq in this case is how many charges in the dx element. I know I have lambda per meter, but I don't have a whole meter. I have just a dx meter, okay? So that's why I'm using this formula. So I know how much charge is sitting in there. So what I'm going to do, because that's what the key is when I said in the beginning, Coulomb's law works only for a point charge. Since dx is so small, I'm going to assume that I'm really dealing with a point charge at this point. dq is a point charge. Okay? Since dq is a point charge, then I'm going to find the electric field produced by dq in that point by measuring this distance. This distance is y, this distance is x. So I know this is, by the Pythagorean theorem, is square root of y squared plus x squared. Probably I'm not saying it correctly because I went to school using the French language, so I still have that in my accent. So I'm sorry about that. It's a Pythagorean theorem. So that distance is y. Man, I couldn't write y with this pen in here. So this distance is y, and this distance is x. And using the right angle formula, it gives me that that hypotenuse is square root of the other sides, basically squared, added together. So that's basically what we're saying in here. So we have that. So we're going to find the electric field, but the electric field is a vector pointing away from that point charge. Here is the electric field. That is a dE. It's produced by just that element. So the dE in this case is going to look like 1/4 pi epsilon naught times the charge. Charge is lambda dx, divided by the distance squared. Remember, I have square root, which I'm going to square y squared plus x squared, times the unit vector r hat. R hat is this unit vector in this direction. Okay? This is on one side. I know also, if I go on the other side, a distance negative x and take another element, it's going to produce this electric field. So both of them, they will be producing an electric field. Therefore, I can think, without actually doing the calculation, that the contribution in the x-axis will be 0, because this one has the same strength as the other one, and by symmetry, because I took a negative x on the other side, is going to be the same. Therefore, they cancel out. The only component that is going to remain is the component pointing away from the wire, and that is in the y direction. So by symmetry, we can clearly see that DEX is going to be 0, or EX, I'm sorry. The total electric field in the x direction is going to cancel, because from every single element on one side, I can always find another element from the other side, and when I add them up, and they will mutually cancel. So when I add them up in pairs, they will cancel. So that's why the electric field in the x direction is going to be 0. So the only component that is going to survive is the one in the y direction, because that's going to add up. Because on this side is going to point upward, and the other side is going to be pointing upward. So when I sum from negative a to positive a, I'm going to find a finite value that is not 0. So the EY direction is going to be not 0. So for me, let me redraw this one. It's getting a little bit too much in there. So I'm going to go back into point A. So I have, this is the electric field pointing in space. This is its component in the y direction, DEY. Okay. I'm going to extend my geometry to see what's going on. This distance is y, and this distance is x. Of course, I extended all the way to positive a, and on this side is negative a. Okay. So I have to find the cosine of this angle, because I'm trying to find the adjacent to this angle. And the cosine of this angle is actually this angle too. So I'm going to call this one theta. That's the geometry. You have two lines that where they cross, they are at the same angle. And here there is a theorem in geometry from high school, basically. So these two angles are the same. So I have to multiply by cosine of theta to find this component because it's the adjacent to the hypotenuse in this right angle triangle. Okay. So DEY then is going to be the DE itself that we found up there times cosine of theta. Okay. That's one thing. So I'm going to go back into my definition in here. By the way, tangent of theta is equal to x over y. You can clearly see that from this right angle triangle. Tangent of theta is equal to x over y. So I can do the substitution x equals to y times tangent theta, basically when I'm doing my integration. So x is equal to y tangent theta from the above expression. X is equal to, from here, then I'm ready to plug in things, okay? Let me go back into my expression here for the electric field in terms, now I'm expressing it in terms of, in the y direction. Oops, this one. In the y direction. So, I have first of all 1 over 4 pi epsilon naught times the charge. The charge, remember, is lambda times dx. Using this change of variables, we can express dx in terms of d theta divided by y squared plus x squared times the cosine of theta. Okay? So now we need to sum this from negative a to positive a. That means we have to sum it in terms of the angles in here. We're going to call this angle theta naught with a negative sign pointing this way to positive theta naught, which is this angle. Okay, I can express my theta naught later on. So I'm going to do a change of variables in here. Have you done integrations already, guys, in your class in calcs?
Yeah, I have. I don't know.
Okay. Are you guys familiar with how to do integrations from your calc classes?
Yes.
Okay, so this kind of basically integral, you're going to see it time and again in this class, by the way. So I'm going to do it probably now and maybe a little later, and even when we do the magnetic field, we're going to see this type of integration. It's almost exclusive always for me to make this change of variable. No matter which geometry I'm dealing with, I'm going to do a tangent of theta equals to x over y. Since I have x squared plus y squared in the denominator in here, I do that all the time. I know that there is probably sometimes easier ways of doing this, but I'm going to do that. And most of the times when we're doing problems in physics and we arrive into an integral, we're not really going to spend too much time on them, assume that you guys know how to do these integrals. But part of the learning process, even in physics, is to do this thing so that they stick. So if when you see me do this, I would recommend that you do the same integral using either this technique or whatever technique you're comfortable with. But the bottom line, you have to do it. And it's better to do it with different approaches because sometimes that's what the integration is. If one of the methods, probably you can't go very far with it, you try another one and sometimes it's much easier and much faster to get the answers to it. So again, I have x equals to y tan theta. So I need to find dx in the numerator. I already have x squared, which is y squared times tan squared, tangent squared, theta squared. And so I need to find what dx is. So dx, in this case, I have y times the derivative of the tangent, which is just a secant squared, times d theta. Okay, so that was not bad. So that answers that. And now I have to express the denominator also. I have y squared plus y squared tangent squared. So again, now dE in the y direction is going to be 1 over 4 pi epsilon naught. I'm going to pull the lambda out because it's a constant. So I'm taking the lambda out. So I'm going to be left with, first of all, a secant squared of theta d theta. Don't forget I pulled the y already. A y came from this dx. dx has a y in it, divided by y squared plus y squared tan squared. I'm going to take the y squared out, and I will be left with 1 plus tangent squared of theta. And of course, times cosine theta. 1 plus tangent squared of theta, that is also secant squared. This is a secant squared, and this is a secant squared, and they cancel. I mean, if you don't believe me, it's very easy to see why 1 plus 10 theta squared is equal to secant squared, because remember from the identity, sine squared plus cosine squared is equal to 1. All you have to do is just add or divide by by cosine squared of theta. You will have 1 in here, and you will have sine squared plus divided by cosine squared, that's tan squared of theta, and that is equal to 1 over cosine squared, and 1 over cosine squared is your secant squared. So this is a secant squared already, and this is a secant squared. They cancel each other, and the whole expression for the E will be a lot simpler than, and don't forget I have a y squared in the denominator, I have a y in the numerator. So one of the y's cancel, and basically what we end up with in this case is dE in the y direction for the electric field is lambda over 4 pi epsilon naught times only one y, because the y and the numerator and the denominator, the secant squareds cancel each other, and I will be left with just cosine theta. And I probably forgot d theta in there, did I? No, it's still there. Okay. So that was the expression for the electric. We need to integrate it, like I said, from negative theta naught to positive theta naught. So the integral of the cosine is just a sine. So this expression for the electric field EY, which is the total electric field, by the way, because now EX is equal to 0. We know that. So the value that survives is this one. So it's going to be lambda over 4 pi epsilon naught y times the integral of a cosine, which happened to be a negative sine of theta. No, I'm sorry, it's a sine of theta. That's what am I talking about? It's a sine of theta evaluated between negative theta naught and positive theta naught. And a sine function is an odd function. That means its value on one side, it's a negative of the other one. But remember, you have a difference, so it's going to add up and give you twice. So the expression will end up having 2 sine theta naught, because you will have sine theta naught minus sine of minus theta naught. And that is equal to positive theta, sine theta naught, because this one there is a minus and the other minus cancel, and you will have 2 of them. So at the end of the day, after all this dust settles, I'm going to write just E now, because we know E is going to be in the X direction, in the Y direction. So E is going to be pointing in the Y direction in this case, and it's going to be lambda over 2 pi epsilon naught. I already canceled the 2 with the 4, times Y times sine of theta naught. Okay? What theta naught, if you're curious about it, sine of theta naught is this angle. Sine of theta naught is A divided by this hypotenuse. So sine of theta naught is A divided by square root of y squared A squared plus y squared. That's it. So that's how much the electric field in the j hat direction, by the way. Okay? Because that's a vector. It's pointing in the j hat direction because there is no x component for it. We just argued that it doesn't exist. Now, if you're curious, for an infinite wire, what happened? When A goes to infinity, when A is super big compared to Y. That means this wire, for example, this is a wire. It's a very long wire. You cannot see it in there, but it's a very long wire. Let's assume, for example, it's a rigid wire that I kind of going to distribute charge on it and so on and so forth. This is about 1 meter away, but if I go very close from it, from any portion of it, I can assume it's an infinite wire. About 5 centimeters away from it, it's infinity. 1 meter or 2 meters is an infinity. So of course, I'm going to neglect the y squared in the denominator, and I will be left with just square root of a squared. So this is going to be dropped because it's negligible in front of a. And I will be left with the a over a, basically, which is 1. Sine of 90 degrees is 1. So at that point, the electric field for infinite wire is going to be just simply E pointing away from the wire to be lambda over 2 pi epsilon naught times however far we are from the wire. So it doesn't drop like 1 over distance squared, but it drops just like 1 over distance. So you're wondering why? I mean, I know for a point charge, it drops like 1 over y squared. I mean, 1 over distance squared. And this one drops just like 1 over distance. Because lambda, remember, is a property of the wire. How many charges do you put per unit length? That's why lambda is constant in this case. It's property of the wire. So even though you have an infinite wire, you're going to have an infinite charge so that the ratio is constant. So in case it drops like 1 over y because as you stretch, there is further contributions from the other side of the charge. So even if you move away from the charge, you cannot go to infinity because the wire is infinite already. But as you start to move away from the charge, you're expecting it to drop rapidly, but it's not rapidly dropping because more and more sides from the wire are contributing toward your electric field. So it's not dropping as fast as you want it to see. So remember, I ask always to discuss your solutions. This is one of the things that you need to have in mind. So we did that. Do you guys have any questions? I know we did it probably extensively, especially the math part of it. No? So we catch this thing. We're going to talk about the ring now, and then we'll take the disk, unless you guys have any questions on this. Okay, so here is a ring, basically. A ring is like a hula hoop, basically. It's like an empty from the inside. It's not a disk, by the way. And you did that, I remember, when at least you should have done that when you were dealing with the center of mass and things like that. One of the things you calculated was for the ring, calculated its moment of inertia and so on and so forth in physics 4A. So this is a ring where the charge now is sprinkled on the edge of the ring. Okay, so that's basically what this is. So there is a charge Q now, and this charge Q is distributed also linearly, uniformly, with the same number on 2 pi r, where r is this radius of the ring. Okay, so that's the radius of the ring. And you're asked to find, in this case, at an x distance from it, the electric field produced by this ring. So we're doing the ring now, we're not doing the wire. So that's basically what the challenge is. So what we do in this case, we know lambda is constant. So lambda is 2 coulombs per meter because 2 pi is just a number. 2 pi is just a number in this case, so it doesn't matter. So we have Q over 2 pi r is my lambda, which is the charge per unit length, which is an arc length in this case. So again, Coulomb's law would not help me. The reason why we did the integral earlier is because we used superposition, by the way. We found it just for an element, and then we integrated, we summed using the superposition principle. Same thing in here. We're going to use an element ds, an arc distance ds. So I'm going to take a ds element, and ds elements on this geometry will have in it an angle phi. So let me refresh your minds a little bit. So this is how the ring looks like when I'm looking at it from this side. Okay, it looks like just a circle, basically. Not a sphere, a circle. So if I take an arc distance in here, ds, sustained by an angle d phi of radius r, then I know ds, the element ds, is simply equal to r d phi. This is something that you also did in physics 4A. Okay? And for the case of a full circle, it's 2 pi r times this basically angle. 2 pi is just the whole circle times r. I'm sorry, to get it for the entire circumference of a circle. So that's where we got the circumference frame. That's how we got that expression, the beginning of the this idea here. So now we know the ds. So an element of charge now on that element of the arc is going to just dq is going to be lambda times ds, and ds is r d phi, and phi varies from 0 to 2 pi. If we go from 0 to 2 pi, we would have gone through the entire ring. So now we have an expression for dq for a single element now. Again, we're going to find the electric field produced by that element, which is this one. Okay? And the idea here also to use the superposition, now we know how to find it for a point charge, to find it for the entire ring by just summing, using the integral in this case, and varying phi from 0 to 2 pi. Okay, that's the only way we're going to do it. Again, there is an angle theta in here. That is the same angle theta in here that I need to be aware of, that I will use. Because if I can take this element, there is always by symmetry 180 degree from that, 180 degree on the other side. There is another element whose contribution is going to be the same magnitude, but with the same angle, but in the other direction, so that this, the y component, now cancels. The only component that is going to survive is the one that is also in the x direction in this case. So this two, they will be pointing in the two different directions, in the y direction, but in the x directions they add up. And that's the one that is going to survive from this calculation, is the one in the x in here. So again, I need to involve cosine of theta. And cosine of theta is simply x divided by the hypotenuse. The hypotenuse from this geometry, again, is r squared plus x squared under the square root. Okay? That's what the cosine is. It's just x divided by that number. So now we're ready to do this. So we set up our problem. We said what we know. We found everything. So we're going to find the electric field just in the x direction, and that's it, because we know that in the y direction there is no contribution. In this case, they will cancel out in pairs, basically. 180 degree from one another in the direction and the phi direction. So dE in the x direction is going to be 1 over 4 pi epsilon naught times the element of charge dq, which is lambda r d phi, divided by the distance squared. The distance squared is this number squared, that's all. Which is r squared plus x squared times cosine of theta. And cosine of theta in this case is just x divided by the same square root of the same number. Times x divided by r squared plus x squared to the power 1/2. That's what square root is. Okay? So I basically have this expression to the power 1 and to the power 1/2, and that is to the power 3/2. That's all. So I could have summarized this and have done it. Now, once we sum through the angle phi, remember, x doesn't change when we go through the ring. How far we are doesn't change. X is not changing. R does not change. That's the radius of the ring. Nothing changes. Lambda doesn't change either. That's how uniformly we distribute. The only thing that's going to change is phi. So the integration here is very straightforward. The integral of d phi from 0 to 2 pi, that is just 2 pi. So the actual calculation in here for E is going to be strictly in the x direction, is 1 over 4 pi epsilon naught times, again, I have an r times lambda, r lambda, times 2 pi, that's coming from the integration, times x divided by r squared plus x squared to the power 3/2. Okay, that's it. That's the electric field anywhere in there. Of course, there are some cancellations due in here. For example, the 2 pi and the 4 pi, you have only 2 left in here. And you can do whatever you want to. Or if you like, you can restore 2 pi times lambda times r. That is actually q. You could say that, and you can express in terms of the initial charge that was in there. But I'm not really going to spend too much discussion on this, other than the fact that it's a little bit easier, actually. The integration is very straightforward. You don't have to deal with the nastiness of the end of first integral. So if we replace this one by q, of course, we cannot remove anything in the denominator in here. So the expression then for the electric field, because that's going to be only in the x direction, is going to be q over, there is nothing taken in here, epsilon naught times x divided by r squared plus x squared, the whole thing to the power 3/2. You're wondering now, if I am very far away from the ring, I wouldn't tell it's a ring at all. I would think that it's probably something far away from it, so it should behave like a point charge. Let's see that. When x is very large compared to r, obviously r squared is going to be neglected. Okay. The only thing that is going to be left in here is x squared to the power 3/2. X squared to the power 3/2 is actually x cubed. So this will be x cubed, And you have an x in the numerator. So you have x cubed and x will cancel. So you will have an x squared, and you will have q over 4 pi epsilon divided by x squared. And that is exactly like it's a point charge, as if there is no, as if it's a point charge. So far away from it, it behaves like a point charge. So this drops like 1 over distance squared, okay? So that's another thing that we just did. And here, that is for the ring. Let's go back in here. So that checks that. Now the disk. So we're gonna go back in here and we're gonna take the disk, which is slightly different. So this is a disk now. Disk is everything. And I know you guys did that. So this is how the disk look like. Have it slightly tilted. It's still a uniform disk of radius r. Okay. So that's basically how the red disk, and again, I'm going to go distance x from it. I'm trying to find what the electric field somewhere next to it is going to look like. The technique here is the following. You're going to assume that the disk is made up of a bunch of rings stretching from little r equals to 0, this point, all the way to when r is equal to big R. In other words, we're going to find the electric field, do it to a ring, and by superposition, again, we're going to add up all of these little rings and sum them up to find the entire disk by taking little r from 0 and expanding it to the entire disk. So again, we're doing the disk now. So we're going to go and find, first of all, a strip in here, because this has a uniform distribution now on an area, not on a line now anymore. And the distribution is Q, which is sigma now, which is Q divided by the area. And the area of a circle is pi r squared. Okay, so that's how much charge we have taken in here. So we're going to take an element dr now, stretching a distance r. So let me redraw that one because it's getting a little bit complicated in here. So here is the small ring of radius little r, where r is changing from 0 to big R, and stretching an element dr. Okay, so a strip, if you wish, of the entire disk. And that strip, if I come in here with the scissors and cut it in here and stretch it, this is how it looks like. Okay, its height is dr. That's this height. And its length is the circumference of this circle, which is 2 pi r. So the area of this strip is going to be length times width, which is 2 pi r times dr. And I know I have spread sigma charge per unit area, but I'm not taking meter squared. I'm taking just this strip. Okay, so the element of this case is going to be dq, is going to be sigma times this area, which is 2 pi r dr. Okay, so let me go back to the expression that I found just a minute ago for the electric field produced by a ring, which is q over 4 pi epsilon naught times this whole business in here. But I'm not taking, this is actually a portion of the entire disk as being a ring. So I'm going to use the same expression, except the charge q now becomes my element charge. So everything should be the same. So an electric field produced by that ring is going to be dE now, because we're going to sum from r equals to 0 to big R, is going to be, again, dq, which is this number, divided by 4 pi epsilon naught, times x, which is the same x in here. That's what we found earlier. Divided by, now r has to change because we used big R for the regular ring, but now r is changing. It's no longer fixed. So I'm going to put little r squared in here, plus x squared to the power 3 halves. R squared plus x squared to the power 3 halves. Okay? That's the only thing that we have to do in this case. We don't have to go through the other thing. The only thing is now we're left with is to invoke the superposition principle and to help us basically sum through all of this r's from 0 to big R. Again, I'm going to put the value of dq, which is sigma. Sigma is how many coulombs per meter squared, okay? But we don't have, like I said, a meter squared. We have just a small strip from the entire disk. So dE then is equal to sigma times 2 pi r dr divided by 4 pi epsilon naught times x over r squared plus x squared to the power 3/2. I think your book does it differently. What it does is it uses the change of variable r squared plus x squared is equal to u, and then finds a du, which is equal to 2rdr, I'm sorry, and replaces the value of 2rdr as being du, and proceeds with the calculation. This becomes u squared to the power 3/2, and the integral should be straightforward, which is fine, which we can do. Or we can use the same technique as I illustrated earlier involving cosine of theta, where we do the r squared plus x squared and basically change the r now is the variable of integration. It's not x. X is fixed. We are at a certain distance from it, and then integrate from the value of theta naught. So whichever technique works for you guys is fine with me. So we're going to follow suit in this case because apparently the change of variable r squared plus x squared is equal to u is a little easier. So that means 2rdr, because x is constant, so we are going to ignore that when we take the differential form, is equal to du. That means 2rdr is exactly du. Okay? So that means that the integral, of course, I have a pi in the numerator and a pi in the denominator, which I should get rid of quickly because I don't need them in this case. And then, so the expression for the electric field in this case, and it's going to be pointing also in the x direction, by the way, because that's how this one turned out to be. So it's going to be sigma times, I'm sorry, did I say E? Yeah, we are going to integrate, so we have to invoke the integral right away, okay? When R goes from 0 to big R, this U changes from x squared to x squared plus big R squared. So you have to remember the limits of integration for U are going to be from an initial value of x squared to a final value of x squared plus big R squared. That's the only thing that we have to remember as far as this integration is concerned. And if we do that and we're careful with our calculation, divided by, in here I am left with 4 epsilon naught. And then the integration is between, this is a bounded integral, okay? So it has an initial value and it has a final value. And I'm left with the x also is constant, so I'm going to take out the x in here. And what else? I'm just trying to see what I'm going to write. And here I have du over u to the power 3/2, okay? I'm not going to put the values and the boundaries of integration because I'm going to store back my values and basically after I find in terms of u. Here in this case, it's u to the power -3/2. You add to it 1, it's going to be -1/2. And you drop by the new power, which is divide by -1/2, which is going to be multiplied by -1/2, by -2. And the 2 in the numerator and the 2 in the denominator, they cancel. And the expression should look like this. E is going to be equal to sigma x over, sorry, there was another x in here that I forgot to, did I forget to do that or not yet? Probably is going to come later on because we still have, yeah, there is a dimensional thing in here that we're going to have. So it's going to be 2 epsilon naught with a negative sign, probably we're going to take care of. And the expression is going to be 1 over 1/2 now, evaluated between those two boundaries, okay? Evaluated between the point u1 and the point u2. So before I do that, I'm going to put this to this expression of this square root basically, so, between the value and evaluate it. So I have 1 over u is the square root of, that's the answer by the way, of r squared plus x squared. Now evaluated between the lower boundary is when r was 0 and the upper boundary is when r is equal to big R, okay? So again, is going to be equal to 1 over square root of r squared plus x squared minus 1 over x. Okay, and because 1 over x is bigger than the other one, so we're going to change the order and changing the sign in there. Obviously, this number is less than the other number because it's bigger in the denominator. So at the end, the expression looks like this. E is going to be sigma x over 2 epsilon naught. And then in parentheses, so I'm going to switch the order and getting rid of that minus sign, 1 over square root of r squared plus x squared. Okay? That's, in a nutshell, what this expression looks like. Obviously, I have the x, which I'm going to take inside now, and cancel one of this x in the denominator. And so E is equal to sigma over 2 epsilon naught times 1 minus x over square root of r squared plus x squared. Okay? That's the answer. Okay? And the limit, when r goes to infinity, when this disk becomes an infinite disk, infinite plate, because a disk or any surface that is infinite is too big to be distinguished from anything. So as long as it's infinite, you cannot tell its boundaries where they are. As if it's a disk or circular shape or whatever shape. So an infinite plate now, infinite plate, basically will have r goes to infinity. When r goes to infinity, bigger than x anyway, so this dominates the denominator. So r squared will become square root of r, and 1 over infinite is 0. So the only thing that is going to be left is 1 minus 0, and 1 minus 0 is 1. So in this case, the electric field of a plate is sigma over 2 epsilon naught. This does not depend on distance whatsoever. We have seen that depends like 1 over distance cubed for the case of the dipole. We have seen things that depend like 1 over distance squared for a point charge. We have seen things for an infinite wire that depends like 1 over distance only for an infinite wire. And now we have seen something that doesn't depend on anything. That doesn't depend on distance at least. So for the case of a plate, an infinite plate, the electric field does not depend on how far you are from it. So if you are very close from the plate, it's sigma over 2 epsilon naught. If you are very far away from it, it's still sigma over 2 epsilon naught. That's it. That's the end of it. So for a plate, does not depend, this is critical, on distance. The electric field is independent of the distance. You see, we have seen a variety of dependence now when it comes to distance. So far, we have done all of them. The disk, the ring, and all of that. The infinite plate, we just did it. I mean, it's just a simple case. All you have to do is take the ring that we found and push r to infinity, and this expression becomes 0. Because it becomes 1 over infinity, and that is 0. So you're now in the case of the infinite plate. For the infinite plate, then, it's sigma over 2 epsilon naught. Now, if you happen to be, and the book brings 2 plates now, so if you have a plate in here and another plate in here, and you sprinkle sigma charge per meter squared on one, and you sprinkle negative sigma charge, that's an, oops, what happened to my, negative sigma charge per unit area on the other one. So in this case, you try to find the electric field in this point above the positive plate. This one will push it away by sigma over 2 epsilon naught. Remember, it's independent of how far you are. It doesn't matter how far you are. As long as you are above the plate, it's sigma over 2 epsilon naught. This one will pull it by sigma over 2 epsilon naught. So on one side, the positive plate will push by sigma over 2 epsilon naught, and the negative plate will pull by the same amount because both of them have the same charge per unit area. The two will cancel. So E is 0 above the positive plate. The same thing is happening below the negative plate. The negative plate now is pulling by sigma over 2 epsilon naught, pulling towards it. The negative plate, no matter how far you are from it, as long as you are outside of it, it's still sigma over 2 epsilon naught, pushing away from it. And the 2 cancel too. So E is 0 outside of the plates. The electric field is outside of the plates is 0. How about inside between the plates? Well, between the plates is this. The upper plate will push by sigma over 2 epsilon naught, and the lower plate will pull by sigma over 2 epsilon naught. So the two of them, they work together between the plates. And the added effect is when you add sigma over 2 epsilon naught and sigma over 2 epsilon naught, you will end up with sigma over epsilon naught. So this device traps the electric field. Outside of it, there is no electric field. Inside of it, there is electric field. So this is a good device to use if you want to trap the electric field in space. So you bring this device with you. Almost all of your electronics at home, including your computer, have this device. Does anybody know what this device is called? You guys know what it's called? Any idea? Sorry? Miles? I'm sorry?
A battery?
It's kind of a battery, you're right, but the battery is slightly different than this one. The battery has a way of making energy. This one doesn't. You have to actually put the charge yourselves. Okay, that's very good, Jaden. That's actually capacitor, condenser. So that's actually any power supply of any of your devices at home. The part of the charging part of it usually has it. So it's a critical component of almost all of the electronics, anything, especially that gets power. So it's actually capacitor. So this is actually a capacitor. So that's what this device does. So it traps the electric field. So if you're interested in basically trapping an electric field, get one of these. Basically, and now outside the electric field cancels out, and between the plates, it's actually, there is a finite value. In this case, it's sigma over 2 epsilon naught. So we're going to come back to this device with vengeance later on when we do circuits. So hold on to this thought in here, so with this point in here. And finally, the electric dipole, we still have about, how many, 25 minutes? More than 25 minutes. So I think we can get the electric dipole also. Any questions before I get into the last point of this chapter? No? Okay, so the electric dipole. I know we introduced it. This is not the same. What we're saying in here, take an electric dipole, which is made up of two charges, a negative charge and a positive charge. Okay? It's the same charge though. And I'm gonna link the two charges with a rod, okay? A rigid rod, so that they don't basically break apart or basically come to one another. So this is rigid. That's a key word, okay? And I'm going to take this entire rigid dipole and put it inside an electric field. So think of this, for example, you have a plate on one side and a plate on the other side, and you have an electric field. So they are inside, so you have a dipole inside a capacitor, for example, the device that we just saw, okay? So you have everything is sitting inside an electric field. So the electric field is everywhere, okay? I just draw 3 lines of it, but you could have the electric field everywhere in space in here. But the point in here is we have a dipole sitting inside an electric field, and we want to find what the effects of the electric field are on the dipole, okay? Obviously, the dipole is made up of 2-point charges. One of them is Q and the other one is negative Q. So this, let me draw with another color in here. So this side will be subject to a force which is QE. Okay? And this side, which is the other charge, is going to be subject to minus QE. So the force is going to be pointing this way, actually. The two forces have the same, the two charges have the same Q, and they're sitting in the same electric field E. So the two forces are the same value. So the center of mass of this rigid structure will not go anywhere, because the sum of the forces that you learned from physics, basically 1, is when you have the sum of the forces equal to 0, nothing is going to happen in terms of the center of mass. It's not going to move. Do you think something is going to happen though? Do we have motion? Can this thing start to move now if we let go of it? Yes or no? This is, again, physics 1 or physics 4A, the one that you took last semester or last year or whenever. Okay, how? Very good, but how? We know the center of mass is not going to budge. And you're saying it's going to move. So how is it going to move? Very good. So now the forces are 0, but the torques may not be 0. So in order for me to have 100% equilibrium, I really have to have the torques also equal to 0. So that's something that you learn also from physics 1. So let's find this torque in here. Again, something you learned in physics 1, where you find the, in order to find the torque, the moment of a force, you really have to choose a center of rotation. Where do you choose the center of rotation? It doesn't matter really. So we're going to take a point, and the easiest point to take is one of the points of application of these forces, so that that specific force has no torque. So I'm going to take this point in here to be my center of rotation. Okay? That way, that force has no torque, because the torque of that force or the moment of that force is 0. So the only moment of force that I'm having in here is this force in here, which is positive Q, making this spin in the clockwise direction, which means it's a negative torque, okay? Trying to go in the negative direction of the angles. So I'm going to find the torque, and the torque of this force is this arm length times the force itself. That's basically what you've learned from physics 4A. And the arm length in here, if I call the angle, by the way, there is something in here that I need to see. We define P, remember, this distance is D between the two charges. We define the P, the moment of the dipole, as being QD. I'm not able to write in that section in there, so I'm going to write it on the bottom. So P, which was a vector, by the way, Q times D. That is, and it's from the negative charge to the positive charge. That's why I made it point in this direction, okay? That's P. That's the dipole moment. So the angle that the E vector and the P vector make with one another, I'm going to call it theta. Okay? So as long as we agree on that angle, we're fine. So now, this angle also is theta, by the way. It's still P and it's still E. This is P and this is E. So that is theta. So the arm length from this geometry is clearly equal to D times sine theta. D times sine of theta. That is in this right angle triangle. So the torque now is going to be the force, which is QE, times D times sine of theta. And it's a negative torque. I have to remember that, okay? Well, Q times D is the magnitude of the vector P. That's all. So this is actually written as P times E times sine of theta. In other words, it's P times E times sine of the angle between them. And tau is actually a vector too. I mean, the torque or the moment is also a vector. It's a 3D vector. So in this case, I have P, and I'm multiplying it by E, and for some reason, the object is going inward, so it's going negative. So the torque in this case, using the right-hand rule, whether this way or, by the way, I think I need to flip this. When we're doing this class, it's very, very critical to bring your right hand. It may look like I'm using my left hand because of this mirroring thing on the screen, but I'm actually using my right hand. So the torque calculations, and you're going to be using extensively that in this class, you have to remember to use your right hand. So if this is P, this is where the E is. So this is where the torque ends up to be. or if this is P, I'm sorry, if this is P, this is where E is, this is where the torque ends up to be. So P crossed with E, and the torque ends up to be in the opposite where the thumb is pointing. So in this case, again, from physics for A, by the way, how to find your directions and things like that. So in this case, what we have then, tau as a vector now is equal to P cross E. That's all. So this is a very important expression that you probably will need a lot, especially in terms of exam time. So you really need to remember this expression. So the last thing that we need to deal with is in terms of the energy. So we find the expression for tau now, which is a vector in 3D, okay? Now, in terms of the energy now, here is the situation. So I'm going to redraw my dipole again. So I have positive charge and a negative charge, and they are sitting inside an electric field E, and I know this vector is P already, okay? And I know this angle. So let me take it in two different steps, okay? I have it sitting right now at an angle theta. Okay, man. I'm going to redraw this if you guys don't mind, okay? Because I want to draw it big, okay? I want to really have this cleared because sometimes this is a little bit confusing and I really don't want to confuse you guys. So I'm going to draw my dipole bigger than this. So here is my dipole. I'm going to draw it in the past. This is how it was in the past at an angle theta 1. And this is where I want to bring it. I want to bring it at an angle theta 2, actually. And somewhere in between them is at an angle theta. Okay? Think of this dipole as it was sitting here in the past. This is how it was. Okay? And I'm trying to bring it to a different configuration so that the new configuration for this dipole, the end game for this dipole, is sitting in here. Okay? So I have to do work because I have to fight this torque. This torque is trying to actually twist it so that it becomes parallel with the electric field. Trying to do it this way. So I have to fight that as if I have, I'm trying to get an object in here that I can drop. This battery, for example. So if I have this battery in here, sitting in here, and if I move it up, I have to fight the force of gravity. So for me to move it up, it gains more potential energy because if I drop it, I will gain more kinetic energy out of it. Same thing with this dipole. It's sitting at an initial angle, theta 1. If I want to bring it to a final position, theta 2, I have to actually do work. And it gains it gains in this case, potential energy. If I let go it should fall back to the position where it's going to be more stable. So that's basically what I'm trying to do in here. Draw an analogy between this one and when we did the case of gravity, when we were defining the potential energy for gravity, or even that of the spring for that matter. You have a mass being pulled by a spring. So if you have it a stretch and you want to stretch it further, you really have to do work against the spring. So that's the same idea in here too. So we have in this case a dipole sitting at a certain configuration and we want to build up more potential energy in it, more energy in it. So we have to spend work. We have to actually do work for that. And work, if you guys remember from physics 4A, is force times displacement for the case of a linear displacement. But this is an angular displacement. So in this case, it's torque times angular displacement. So the infinitesimal amount of work in this case, dW, is going to be the torque, tau, times the displacement. And the displacement is this one, in this case, is an angular displacement, d theta. But it's a negative work because I have to do it myself. I have to actually fight the configuration right now. Just like when I have an object sitting in here and I want to push it up, the force of gravity is pulling down and the displacement is upward. So in this case, the scalar product of the force times the displacement is going to be a negative number because the force is pointing down and the displacement is upward. Same thing with this one. The torque is counterclockwise, clockwise, and the displacement is actually counterclockwise. You guys understand that? As long as we are clear on this, because the torque is actually pointing clockwise, that's where the torque tau is, and the displacement, so it's a negative direction, and the displacement d tau
is the theta, I'm sorry, is actually in the opposite direction, counterclockwise, where it should be, the positive direction. So if we have that cleared, and I hope that you guys don't have, if it's still vague, please let me know, okay? Because I really want this to be understood. So if we have that, then it's a matter of just subbing the value of tau. We just found what the value of tau is. It's PE times sine of theta. And we sub the value in there. So dW, and the amount of work just to make the d theta displacement is going to be minus PE times sine theta d theta. Of course, we're going from theta 1 to theta 2. So we're going to integrate this expression from theta 1 to theta 2. And minus sine theta is actually cosine theta when you integrate it. So the work is going to be PE times cosine of theta evaluated between the initial and the final position. So it's going to be cosine of theta 2 minus cosine of theta 1. So that's basically what the whole thing is. Okay, so the work in this case is going to be PE cosine of final minus cosine PE cosine of theta 1. And in this case, I can assume that there is a position for every single position, because now this final and initial expression doesn't depend on the path. That means that this work is actually path independent, and the energy, and this can be associated with the potential energy. And the potential energy is just this expression. So P, with a negative sign, by the way, because we have to do this expanding from it. So the P at the end. The potential energy in this case associated with the height, which is going to be minus P times E times cosine of theta. Because remember, the work is actually U1 minus U2. So if I define this one as the value, the initial value, so I have to put a negative sign at the end, okay? Because this whole work has to be a negative work, the one I am expanding. So at the end of the day, these are vectors, by the way. P is a vector, E is a vector, and cosine of theta is actually in the angle between them. And the potential energy, this is what it is. The potential energy is a scalar, is a number. Since these two vectors, and they involve the cosine between them, that means the potential energy is minus P times E. The scalar product of these two, okay? Not the dot product. I mean the dot product, not the cross product. Because at the end of the day, the energy is actually is a scalar, is a number. Okay, it's going to be expressed in joules. Okay. I cannot emphasize how important this expression is. And then the one that we found above for the torque are in terms of later on applications. Okay. So this expression and the expression we just found in terms of applications, because once we get into the motors, and they involve actually a different kind of dipole, it's a magnetic dipole actually, not the electrical dipole. They will also involve torques, and they will also involve energies, and you're supposed to calculate torques and everything else. So even if trying to understand the mechanics, for example, of how an electrical motor works, it relies on the dipole. As a matter of fact, the electrical dipole is very, very crucial when it comes to magnetism and understanding the magnetic field. Any questions, guys? Okay, again, this is going to be, it's actually recorded. So I'm glad it is. So hopefully you guys go through it. The same discussion actually is in the book. I try to draw parallels. Usually I don't, honestly, but in this case I did a little bit because I wanted to stick as much convention as you guys use in the book, so that you will find different resources so that you can do your work. So this chapter is actually fully developed. I don't think that we missed any part of this chapter. All the content we're supposed to cover, we covered it. Depending on how fast we're going, we may have to do some applications down the road, some problems like I promised before, where we discuss them. Again, this is not the first week is not going to have problems where you're going to be asked to do them in the post discussion. I know some of you asked me, what are we supposed to do? You're not supposed to do anything at this point. The only thing you're supposed to do is make sure that you're doing your work on Canvas, and I can tell that by just basically logging into Canvas and seeing that you're actually working on your stuff. So I'm going to do that as part of your first week participation. However, down the road, that's not going to be very clear for me where you are in terms of the material. So that's why I would be asking specific questions during the live sessions, during the synchronous sessions, that immediately once the discussion board is made up, so that you can go and answer 1 or 2 or up to 3 questions basically related to that live session. And that way you're covered your participation for that. So for this week, you're going to get all of your credit. You don't have to do anything. I'm hoping that you go there, please, and ask questions if it's in the discussion. That's actually the purpose of those discussion sessions that come after the live sessions, is that you go there, and if there's a question, please ask it there to clarify things, or basically expand on things, or add to things, or raise the point that the book has done it differently than what we did in lecture, and which one you find a little bit better for you, which is fine, and which one needs to be clarified, or which example, for example, you're still struggling with because I didn't. One of the things that you're supposed to do, and it's part of your to-dos, is to do all of those examples I mentioned on Canvas. So you're supposed to go and actually do those ones. And if one of them is giving you a hard time, or you're not seeing it exactly how it was done, please let me know there too in the discussion. And if I don't jump in and answer your question in the discussion, anybody is welcome to answer it. That's the purpose of actually of also the discussions. The only thing in here usually is you have to really come in and basically be respectful and mindful to the fact that you're addressing another person. That's why the first activity is critical also, in that you introduce yourself, how people need to address you, give them a picture so that they put a human element to it, so that they know that they're dealing with a real person. And they come in and say, no, actually, this is how I thought it was done in the book, or this is how we thought it was done in the lecture, and maybe that answers the question. And we can all learn from one another. I don't claim to know everything. That's one thing that is very important for a scientist, is to have humility. Any questions so far? Thank you, Ed. No? Well, chapter 1 is covered, or chapter 21, okay? Don't forget you have a homework assignment for this chapter. You will have quizzes in this class. And so please take care of things and ask me if you need me to do things differently to make the material a little bit easier for you guys. See you guys on Monday. The link for the sessions is actually on Canvas. It's on Compare Zoom. We will have the instructions for the lab hopefully by Sunday, or this weekend. You will have the instructions. The lab is going to be on Canvas. The link is going to be on Canvas. The lab is going to have activities where you're going to complete things. And that's it. And I'll see you Monday. Thank you.